Problem 12.10 is a typical population type of problem with exponential growth. You should be able to do these. There will be one in the next quiz, probably one in the next midterm or final. These kind of problems you just need to know how to do. So it's a good representative example. 12, 12, 12, 11, 12, 9, they're all similar types of things. Okay, so you just need to know how to deal with these populations. Okay, so let's look at 12.10. It says the populations of termites and spiders in a certain house are growing exponentially. The house contains 100 termites the day you move in. So that's T0, right? Starts off, we know at time 0 there's 100 termites. And 4 days, the house contains 200 termites. And then they start talking about spiders and other things. So let's figure out the termites first. So at T equals 0, the number of termites, I'm going to use capital T for termites because little t is for time. We don't want to get them confused. So capital T is for termites. So the number of termites, so that's T0 is 100. So T0 is 100. And at T equals 4, where we're measuring time in days, I believe, yes, days, it's 200. So T is 200. You need 2 data points. You need to know 2 things for an exponential model. You need to know 3 things for a quadratic, but only 2 things for an exponential model or for a line. Okay, so we know our 2 things, so now we can model it. Now, one problem we have to figure out is, do we want to use the E to the AT model or the B to the T model? And either one works. You should get the same answer, so it doesn't really matter. So we have to decide that, so you kind of choose your favorite because the answers will be the same. I'm going to use the B to the T model. Okay, that's typically what they use when they solve things, except if there's a reason why you want to use the E to the AT, like if they give you the continuous growth rate. But we don't have any growth rates here, any continuous growth rates here, so it doesn't matter. Okay, so T0 is 100. If they give you T0, that's the easiest. Sometimes they say after 4 days it's this many, after 8 days it's this many. You don't know what T0 is and you have to solve for it. But they gave it to us, so that's good. So we know that our model is T is equal to 100 B to the T. Now we got to figure out the base. Again, we could say E to the AT, and then we figure out A. We don't know one thing, either E to the AT or B. Here we don't know B because I'm going to use this model. But we do know one point. Plug in 4, we get 200. So 200 equals 100 B to the 4th. Okay, let's move the 100 over here. So that would just be a 2. So 2 is equal to B to the 4th. We want B, right? Not B to the 4th. So we take the 1/4 power on both sides. So 1/4, 1/4. So what is the 4th root of 2? That cancels out. So B is equal to the 4th root of 2. So B to the 1/4 power. So I'm going to need a calculator to do that, which means I have to find my calculator. Right where it should be. So if I go 2 to the 1/4 power, and I get 1.1892, 1.18. I'm going to keep all those. So, because you want to keep a lot of decimal places, because if you're off a little bit, it actually makes a big difference. I can. So 1.1892. Why did I put 0? 1.1892. Is that right? Well, okay, good. So, that means now that we can say that our formula is, finally we know the number of termites. The number of termites is 100 with 1.1892 to the T. Okay, good. That's the number of termites we have. Okay, now we want to figure out the number of spiders, and then what we really want to know is how long does it take the population of spiders to triple. So our answer is about spiders, but we had to figure out termites to get spiders, okay, because they're going to be all clever with us here. So here's their cleverness. 3 days after moving in, there are 2 times as many termites as spiders. Now okay, our spiders now are going to be S0 new B to the T. Okay, so that we're going to have to figure out S0 and B. They don't tell us S0. They don't tell us how many there are in day 1 or in day 0. They tell us how many there are in day 3. So 3 days after moving in, there are 2 times as many termites as spiders. So let's write that out. So when T is 3, this is, okay, it's so complicated. 3 days after moving in, there are 2 times as many termites as spiders. So the number of termites, okay, so 2 times as many termites, 2 times as many termites as spiders on day 3 when T equals 3, right? On day 3, the number is 2 times as many termites as, so whatever the number of spiders, oh wait, see, this is wrong. I always have to think about this. 2 times as many termites means that the number of termites is 2 times the number of spiders, right? There are 2 times as many termites as spiders. More termites, there are more termites. 2 times the number of spiders is termites. It's really tricky. I get this wrong a lot, and you've got to really think carefully about this. I know a lot of people get these things wrong on tests, so think about that. 3 days after moving in, there are 2 times as many termites as spiders. There are more termites, so the number of termites is twice the number of spiders. Okay, that makes sense now. Then they say 8 days after moving in, there are 4 times as many termites as spiders. So it looks like the termites are growing faster. 4 times. So when T equals 8, the number of termites is 4 times the number of spiders. Okay, so those are our 2 data points. Now we know the number of termites. We can figure out the exact number of termites when we know the time. So these are numbers, and then we can use this to figure out the number of spiders. Okay, so let's figure out the number of termites on day 3. Okay, so we need day 3, we figure out the number of termites. So on day 3, this is 101.1892 to the 3. So now it's a calculator problem. So I'll go figure that out. So times 100. And I get 168.179. That's about 168.18. Now you can't have a fraction of a termite. So here's a question. Do we round off to 168? Actually, this is the number of, this is the number of termites after 3 days. You can't have a fraction of a termite, but this is a model. So I think we want to keep the decimals. We don't want to round off, even though it makes no sense, right? So this is 168.18, the number of termites. Now let's figure out on day 8. Change that to an 8. And how many do we get? So we have 1.1892. Raise it to the 8th power. Hopefully you're getting good at doing that. That's about 4 times 100. That's 399.98. That's practically 400. That's practically exactly 400. So I'm going to say they're exactly 400, which is nice because we don't have a fraction of termites. So that's how many termites we have. This is the number of termites. So 2 times the number of spiders. Okay, the number of spiders is half the number of termites. Okay, so this is the number of termites. The number of spiders is half that. Spiders is half the number of termites. So it's 2 times as many termites. So divide that in half. Ooh, can I do that in my head? 84.09. 84.0. I think that's right. Half the number of termites. Here it's divide this by. Oh, whoa! I can do that one in my head. 400. The number of spiders is 1/4 the number of termites. Right? There's 4 times as many. Wow, that's pretty nice. So now we have the numbers at the times. So now we can figure out using this model what they are. Okay, so let's do that. We have 2 equations. The number of spiders is S0B to T. So spiders is 84.09 equals S0B, and the T there was 3, B to the 3. Another equation is 100, there's 100 spiders, 100 spiders equals S0B to the 8. Day 8, there's 100, day 8, day 3, there's 84.09, because that's what we figured out over here. Phew, okay. We need to figure out how many there were in day 0 and how many there are and figure out B. Once we have the model, then we can figure out anything we want, like when will it take the population of spiders to triple. So we got to figure out our model, this model, to then figure out when it's going to triple. Okay, so let's figure this out. First thing you do is divide these 2. Okay, so let's divide these 2. This is real easy. This one divided by that, I can do that in my head. So if we divide those 2, 84 divided by 100 is just 0.84, so 0.8409. S0 divided by S0 goes away. B third divided by B the eighth, so that's equal to the S0's canceled. B third, yeah, I'll just write it out. B the third divided by B the eighth. Okay, now that's B the negative 5. So I'm going to continue here. 0.8409 equals B to the negative 5. But we don't want B to the negative 5. We want B to the 1. So let's see. Or let's do it this way. Well, yeah, we can do it this way. Okay, let's just do it. Let's just be clever. So we raise both sides now. Let's raise this whole thing to the negative 1/5 power, because you guys are so good now with exponents, right? So to the negative 1/5 power, because negative 1/5 times negative 5 is 1. That gives us B. So if we do that, we get our B over here is equal to 0.8409 to the negative 1/5. Now it's a calculator problem. Plug in 0.8409 to the negative 1/5. 0.8409 y to the x. 1/5 is 0.2. 0.2 negative. Yep, that's right. And I get 1.0. Okay, how many decimal? I can keep a lot of decimal places. 1.035264, which is 1.035264. That's a lot of decimal places. Oh, what the heck? I'll keep it. That is the base. Now we know the base. Now we got to figure out S0. Okay, we can use either one of these equations to do that. I like the 100 one because that's a nice, pretty number. Okay, so I'm running out of room here. Let's see. Okay, I'm going to do it over here because we don't need this information anymore. We don't need to know about termites anymore. Once we get our spider model, we can figure it out. So we used all this to figure out termites. We use the termites to figure out spider model, and then we use the spider model to figure out the tripling time. Okay, but we're not done the spidering model yet. So far we have that the number of spiders is S0. The base is 1.035264 to the t. And now all we gotta do is use one of these points to figure out what S0 is. So let's use the 100 like we said. So 100 is equal to S0 times 1.035264 to the eighth. Right, our base is this. It's 8 days. We have 100 spiders. So now we can figure out S0. So S0 is just 100 divided by all that, divided by all this stuff here. I'll write it again. 0.035264 to the 8th, which equals, here we go, it's really exciting, 1.035264 to the 8th, 1 over times 100 equals 75.786, 75.786, good enough. 75.786. So we started off on day 0 with 75. Okay, again, you can't have a fraction of a spider, but this is a model, you know, we want to be kind of precise. Started off with 75.786 spiders. So finally, our model is, the number of spiders is starting off 75.786, this big huge number, 1.035264 to the t. That is our number of spiders. Now we know how many spiders there are anytime you want. It starts off 75. At 3 days, there's 84, grows a little bit. After 8 days, there's 100. Not growing really fast because this number is not very big. That B number is not very big. Okay, finally, we want to know how long does it take the population of spiders to triple? What is the tripling time? Okay, so we don't need any of this stuff anymore because we have our formulas. We know everything we want about termites and spiders. So now we don't care about the question asked about spiders. Okay, so when will there be 3 times as many? Okay, so what we do is we plug in 3 times as many. So we need to know what 3 times. We start off at 75.786. We want to know when are there 3 times that. So I got to know what 3 times 75.786 is. So that number is about 227.36. 227.36. So when will there be 227.36 spiders, which is 75.786 times 1.0, oh my gosh, write this over again, 35264 to the t. What is t to make this true? That's what we're looking for. Now, okay, let's move this over here. We know we're going to get 3 because this is 3 times that number. So I really didn't even have to do this. I can just move it over and get 3 or whatever. But okay, so divide both sides by that. We have 3 is equal to, I'm not going to copy the number again, that number to the t, that 1.03 number to the t. Oh, okay, I'll write it. 1.035264 to the t. We want t. How do we get this t out of the exponent? Let's see. We have to use some clever things, right? So the way you get out of exponents is to use logarithms. The way you get rid of exponents is to use logarithms. You could use the log base 10. Most of the time, just use ln. Seems to be the best. I don't know. So ln of both sides. ln of 3 is equal to ln of that number, 1.035264 to the t. The point of this is the t then can come down. So ln of 3 is equal to t ln, okay, I'm not going to write that time to that number. So t is the ln of 3 divided by the ln of this number. So finally we can figure out what the time is for them to be triple. What is the tripling time? How long and how many days it takes to triple? So I go 3 ln divided by 1.0356. Gotta get that number right. 3 ln divided by 1.035264 equals 31.7. I get 31.7. So about 32 days. So that is the tripling time. Now it turns out when things grow exponential like this, that's how long it takes to triple no matter where you start. From day 1 or day 0, from the starting point, we said there's 75 spiders to start off with, and then when are there going to be 3 times that many after day 0, when t is, and we get 31.7. But no matter where you start, turns out that will be the tripling time. And 30 days, if you have so many spiders, when they're going to be triple, in 31.7 days, there will be triple. So the tripling time is 31.7 days. Okay, so tricky problem. We had to figure out termites to figure out spiders. Then we had to use the spider formula to figure out the tripling time. Lots going on there. But that's kind of how you do these. Again, you don't have to use the b to the t. You could use e to the at. The advantage of that is the a kind of gives you the continuous growth rates, which is nice. In this case, we didn't really care about that, but it's kind of nice to know. Now the b gives you the growth rate too. Okay, the bigger b is, the faster it grows. It turns out, if you want to look at the growth rate at an annual or at a daily basis, which it actually works that way, that this number here is the growth rate at the end of every day. So not continuous, but at the end of whatever the time period is you're looking at. So it would be 3.5% per day or something like that. Yeah, so that it does kind of make sense. This number does tell you like the daily growth rate, the decimal here. Tells you how much faster it's growing a day. I'll talk about that more in one of the other problems. But okay, good. There you go. Hope that helps. Tricky problems. You got to use lots of paper and don't try to cut corners. Show lots of work. Make sure your answers make sense because there are so many places to go wrong. So always check and make sure things make sense. And things seem reasonable. And check your work. Yes. Okay. Goodbye.